All right, it's time. Before we continue, I had a conversation with one of my students yesterday, and we were talking about something called the Relux triangle. Have you guys seen something like this before? It's a pretty cool concept. So you can create something which is almost like a triangular shape by drawing three identical circles like this. Okay, the center of the circle is actually on the edge of the other circle, the other two circle actually. Okay, so if you draw that, you have a shape like this, and this shape has really interesting properties. Okay, it's called a Relux triangle. The special thing about this one is if you rotate it according to a small circle, the thing drawn by the edge, by the vertex, are exactly something very similar for as a square. Okay. Now, if you think about applications, then you can basically take a drill, and now you can draw some square hole. That's pretty amazing if you think about it. Like if I ask you, like, can you draw a hole which is square? You say that's impossible. If I am doing rotation, I'm definitely going to have a circle, no matter what, right? Okay, but this one actually can do something like this. Now another application, if you think about it, because it stays in a square, that means if you just take this thing as wheels, the whole thing will actually keep the same height as you move. So you can use that thing to move things. And they stay the constant height. Okay. If you are stupid enough, you can actually use that thing to build a bicycle. It's pretty slow. But the good thing is you will never feel like this guy's going up and down, right? It's actually not vibrating because the whole thing stays constant height, just as a circle. Okay. Okay. And finally, that's where our conversation originally starts. We were talking about rotary engine. Okay. The key part of rotary engine is you need to want some kind of like a Rolex triangle inside. So the beauty about this thing is within one rotation, you can actually combust that thing for 3 times, compared to normal engine, you can only do it for 1 time. So in this way, you can actually add up power really quickly. Okay, that's why people use this kind of thing to build race cars. Especially Mazda is famous for their rotary engine. Of course, the drawback is this one consumes gas like crazy. It's not so efficient, and the parts wear out really easily. But if you just need some racing car, okay, so rotary engine is actually a very popular selection. Now let's see the real ones. See, one rotation you can boost it for 3 times, which is way better than normal engine. Here's the yeah. That's everything about the Rolex triangle we talk about. So that was a really interesting kind of conversation. We were talking about cars, and somehow we're talking about rotary engines, and then suddenly something mathematical just come out of it. It's a pretty cool concept. All right. Before we continue, well, let's go over the homework first. Is there any question from homeworks? Aaron?
4.8, number 2.
.8, number 2. Oh yeah, this one. I'm going to remove this one, and I am going to remove the other one, which is number 4. The reason is because you guys get the right number, and Weber gets the wrong number. So Weber was wrong. Okay, as long as you get the first part right, you're on the right track. The second part, Weber could just get it wrong. Okay, so remove from Weber. All right. Now, Nathan?
4.9, number 2, please. Okay. That's no. Yeah, find the antiderivative. Okay. Number 1, you see the word general. Basically, general means you want a plus C there. A specific antiderivative means not only you have a plus C, you know what C is. Okay, so just plus C means general. Now for antiderivatives, clearly you have x times 4 minus x squared. As we said in class, for multiplication, it cannot be so straightforward. Okay, we need something else. Luckily, there's a way for you to avoid multiplication. That is, you can actually just distribute everything. So in this way, you don't have multiplication anymore. You have 3 individual parts, and each part you know the derivative, antiderivative. Then you just sum them together. So the capital Fx you're looking for is general, so plus a C. Yeah, that's how you get this one. All right, Anton?
Yeah, so I was kind of having trouble with 4.9, number 4.
4.9, number 4. Suppose, find the general, okay. Again, find the antiderivative of so the key here is, again, we don't know the quotient rule, but we can split them into several. That's a 4? That's a 4, okay. Okay, more precisely, this is 6 times 1 over x. Now let's do the antiderivative for each one of them. Ln, absolute value of x plus a c. So together,
Kind of as a follow-up to that, why would it be natural log of x? Wait, why could you not say x to the -1 and then make that, because that's what I did. I said it was x to the -1 and then I added 1, making it 0,
which is 1.
which is 1, and then I just had like a
What's the derivative of 1?
0.
Is it x with -1?
Oh,
Not really, right? So that's why like every single power works except for 1 over x. That one is attached exactly to ln x.
okay.
Everything else, you can just feel free to add 1. And the reason is because if you have add 1, you got a constant, and clearly that one doesn't work.
Yeah.
Okay, we have something else.
Okay.
By the way, doesn't that make you wonder, like why? I have a whole family of powers and suddenly ln x just show up. Think about it. It's a very interesting question. You need to think about. There are some deeper connections between ln x and the power functions, even though ln is not a power. This bothered Isaac Newton for a long time, by the way. All right. Anything else? All right. Before we continue, next week will be the Thanksgiving break. We will not have a class starting from Thursday. We will still have classes on Monday, Tuesday, which is supposed to be Thursday, and Wednesday, which is supposed to be the Friday's class. Okay. Number 2, usually at this point of the class, on Wednesday, a lot of people just leave their dorm and go and drive back to the home. So a lot of them cannot make it to the class. So I checked with the first section, and more than 25% of them said they won't be able to show up on that day. So I decided to cancel the class for that class. Okay. Will you guys be okay with that if we don't have any classes next Wednesday? Okay, so let's take a break on that day. But if you chose to stay here and you chose to come to the class, you have some questions, then feel free to send me an email ahead of time. I can meet you during that time because I am free. Okay, but I will leave it to you. I won't show up as a default, but if you ask me to show up during that time for some questions, I will be more than happy to help you with that. Okay, so no class. Next Wednesday, which is supposed to be 11/25/2020, due to the Thanksgiving break and people driving home. Okay. If no question, let's continue. Area under the curve. Something like this. Okay, we have the area under the curve, and this is our plan. Number 1, we divide them into small intervals. Number 2, we take this part. We try to calculate what is each area. Of course, it's not accurate. It's not easy, so we change it to be a rectangle. We change it by taking a sample on this rectangle. We can do it whichever we want. We can do the left point, right point, midpoint, or any point. Okay. After that, we do a Riemann sum, which is nothing but just adding all these rectangles together. You have a number. And finally, we let the number of rectangles goes to 0. That will be our area.
That's the logic. We find two things. Number one, it's very difficult to compute. So if possible, please give us an alternative way to do it. However, if you just want an approximation, a computer will be more than happy to do all the squares for you. Okay. Second, this is a limit, and the limit does not always exist. Okay, so limit may not exist. Then, of course, the next question is, when does it exist and when does it not exist? Okay, do we have a way to check? Do you have a way to guarantee that we have a limit? And the answer is yes. That's where we have the upper sum and the Riemann lower sum. Okay, it's quite easy. For upper sum, lower sum, we just have a very special way to sample the points. Assuming the whole thing look like this. For upper sum, for every single rectangle, you don't take a random point. You always take the maximum for that small interval. That's how you calculate the upper sum. For lower sum, you always take the minimum. Okay. Once you have done that, no matter how you sample the points, it will be always bigger or equal than the lower sum, because lower sum always underestimate what's going on. You take the minimum, and everybody else is at least as good as the minimum, and maybe higher, right? And the upper sum is always an overestimate, because you always take the maximum. Everything will be at best the same, but usually below. Okay? So how do you make sure that the limit always exists regardless of how you sample the thing? You just want the limit of this one exist. By looking at that, I think everybody figured out that's squeeze theorem. It will be fine as long as the upper sum equals the lower sum if you take the limit. Okay, this is according to the squeeze theorem. Sounds good? Okay, this is, again, in general, difficult to check. Are they the same or not? But this is just like an idea. Like, if you know how to check it, you can guarantee that your Riemann sum exists. Of course, we want to give you a really bad example where Riemann sum does not exist. That is the Dirichlet function we talked about before. If x is irrational, if x is rational. Okay, and then we want to find the area of fx, okay, on 0, 1. Try to recall what we had before. This thing is not even continuous. Okay, the reason is because the graph roughly looks like this way. It may look like there are two lines, which means this one is not a function. Okay, but actually, all the lines are separated. All the points here are separated. It's just they're so dense that I cannot draw them separate. Sounds good? Because every time you pick x, it's either rational or irrational. So you either pick 0 or pick 1. You never pick both. Okay? Therefore, it's still a nice function. Now I'm asking, what's the area between behind this, under this? Now think about how you're going to do it. You're going to start to cut them into small pieces, right? Then you take out a piece, which roughly look like this. Okay. Now let's take the Riemann upper sum. What's the Riemann upper? Hold on. The width is 1 over n. Okay. For upper sum, you need the maximum. What's the maximum in this interval for this function? Always 1.
Why? Because there is always at least one rational number inside this interval, no matter how small it is, right? Make sense? Okay. Hold on. I was signed out. I have to sign in again. Am I signed in? Okay, I'm signed in. Okay. Can you guys hear me? So I guess I'm not disconnected. There may be something wrong with my recording. All right, so you have the maximum. What's the minimum? 0. Why? No matter how small the interval is, there's always a irrational number in. So I can always achieve a max minimum, which is 0. All right. So what's the Riemann upper sum? The length, the width, times the height. The height is the maximum, which is 1. What's the lower sum? Which is always 0. No matter how many different rectangles you divide, it's always 0 for lower sum. Okay. What about the upper one? Well, the upper one is going to be 1 over n plus 1 over n plus 1 over n plus 1 over n, because every term is 1 over n, right? And how many terms do you have from 1 to n? There are n terms. Okay, so what's the total? The total is 1 over n times n, which is 1. Make sense here for the calculation? Okay. Now, no matter what you do, no matter how many rectangles you have, you either have 1 or 0. Now, here comes the question. What is the limit? Well, it's pretty easy to see. They don't even change as you change n. So limit is, of course, 1. Limit n goes to infinity, of course, is 0. Are they the same? Therefore, squeeze theorem doesn't work. Therefore, cannot use Riemann sum. Why? Because depending on how you sample the point, your answer will be different. So what's the area? You cannot say it depends, right? It should not depend on how you sample the point. So from here, you can see for this example, Riemann sum fail. Sounds good? Okay, so we do have those kind of concerns. Not, luckily, for everything we have in normal life, usually it's doable. Okay. Then back to the question we had before. I mean, this function, we cannot do Riemann sum, I understand, but this function is not so bad, right? It's not too bad either. We should be able to find the area. Now let's take an alternative approach. We're not going to touch the details of it, but let's just see if this makes sense. You were trying to find an area here, right? You really don't like it because some of the points here, they are 0. Meanwhile, somewhere they are 1. Okay, they're just jumping around. That's why you cannot actually find a fixed point, a fixed area. Good so far? But if you think about it, isn't that nice? If magically, you don't really care, right? You just push all the rational numbers between 0 and 1 to the left-hand side. And then you say all the irrational numbers go to the right-hand side. That's doable, right? You just move the location, okay? Somehow here, everybody rational will be here. And everybody irrational will be here. But now what happened? You guys all stand together and you guys all have 0. Right? Now you guys all stand here and you guys all have 1. Make sense so far? So in this way, I could be able to find the area of the under this curve, and the area actually equals 1. This part is 0, so there's no area. 1 times the length of all rational numbers in 0, 1. It really depends on how wide that thing is, right? And how wide is that really depends on how many rational numbers are there in 0, 1, because you let them all stand to the left. If you know how many, period, you know how long it is. And then you know how the whole area becomes. Good so far? How many numbers are there in 0, 1, rational numbers? Infinitely many. But like we said before, does it mean that the length is going to be 0? Not really, because we do know this fact. All numbers in 0, 1 has a length 1. Everybody agree? That's the length of the interval 0, 1. Right? Okay. And you have to agree, you only have rational and irrational. So I don't know how long you guys are, but if this plus that is going to be 1, because you guys together are going to be 1. So you guys cannot be infinity. You guys cannot be 0 either. Otherwise, you plus together is not 1. You must have some length. Sounds good? Okay, so that's the whole analysis behind this. Now it narrowed down to how many rational numbers are there and how many irrational numbers are there. Do we have more rational numbers than irrational numbers? Or do we have more irrational numbers than rational numbers? Or are they the same? If they're the same number, then it's easy. Then this is going to be 1/2. This is going to be 1/2 because you guys together are 1, right? Okay. If this one's twice the size, then you're going to have 2/3 and 1/3, right? So it's really narrowed down to how many irrational numbers are there and how many rational numbers are there between 0 and 1. Okay. I will leave it here, but this is an open question you can think about. Who has more number? How much more? How do you even quantify, because both are infinity? You're basically trying to say one infinity is way bigger than the other infinity, or maybe two infinities are equal. Okay, either way, think about it. Feel free to Google it and try to see how people attack those kind of questions. It's very, very interesting. All right. That's everything about Riemann sum we have done. Now we want to go to definite integral. We want to find a better way to calculate the Riemann sum. But before that, let's first try to study the area a little bit. If you have noticed, I've written this thing for multiple times. Okay. Which is really a pain in the butt. You write a whole sentence, which means the same thing. You better give it a notation, which is easy. Just as I don't want to write down the derivative of fx every time. I just say, hey, f prime. You know what I mean, right? We want a better notation for this, okay? What are the useful information? Well, you need to tell people what fx is. You need to tell people a and b. Those information has to be in the notation. Second, somehow this notation should also reflect how you calculate it, right? How do you calculate things like this? That's going to be sum. Okay. Delta x, well, delta x is the width. This is the height. Then if you look at it, you say, oh, it's a lot of rectangles together. And finally, you want limit n goes to infinity. That's how you calculate the area. Good so far? You want a notation to reflect this sentence. Meanwhile, it should reflect how you calculate it. Think about how you're going to design that thing. And Leibniz has designed that thing for us, which looks like this. And that is called a definite integral.
Number one, the notation look like this. Let's try to see how great this notation is. Number one, at least it looks simple. And it kind of looks nice, right? It's not too ugly. Does it tell you information about fx? Yes. Does it tell you the information about the starting and ending point? It's right here. Okay, so everything in the sentence I want to say is contained here. You know which interval I'm doing. You know what function I'm doing. Sounds good? Second, does it reflect this formula? Well, you have a delta x, right? I have a dx. Looks familiar. We have dy over dx. Where does it come from? It comes from the change of y divided by change of x, which is delta y over delta x. We let n goes to infinity or delta x goes to 0, it becomes dx. This one feels so natural. Sounds good? You do have a sample point of fxi, which is the height. I do have the sample points here, but I don't have the sample anymore because my rectangle becomes super, super narrow. You pick the starting point, it's the same as the ending point because I'm not taking the rectangle anymore, I'm taking a line. So I don't need xi star anymore. Still okay? Very good. So fx star delta x, it got recovered from this formula, which is really nice. You have a sum sign, which you cannot do anymore because if you use sum, you also have to tell people I'm taking the limit n goes to infinity. So these two symbols together, you want to develop the sum, write it in a different way, but still mean it's a sum, but it's a sum when n goes to infinity. That got merged into this sign here. This means not only I'm taking the sum, I'm also taking the limit for n goes to infinity. Make sense so far? Okay. So what do you think this symbol stands for? Where does it come from? Every symbol has a, for example, if you do music, you have something like this, right? So every symbol has an origin. What do you think this is? It's a letter. It's the letter S. What does S stand for? S stands for sum. Okay, so basically they just take the letter, they take the sum, and take the first letter, stretch it so you have room for the starting and ending point. Otherwise, this looks pretty, it's not too bad, but not as good as this one. Okay, it's beautiful. If you look at this one, it's simple and it's elegant. So I really like this symbol. Okay, ancient Chinese was really good with numbers. Okay, but they never developed very advanced mathematics. Do you know why? This is how we write all the numbers. This is 1, right? In Chinese character, this is 1. This is 2. And this is 3 in Chinese character. What do you think 4 is? It can't be that. This is 4. 5, 6, 7, 8, 9, oh no, and 10. Okay, on the left, you got all the Arabic. On the right, you got the Chinese characters. And these are simplified versions for modern versions. Do you know the older version? This is 1. Okay, this is 2. This is 3. What is 4? 4 is this. Are you surprised that Chinese didn't actually develop a very complicated number system? Okay, this is how we write down 10th, I don't know. This is how we write down 12,035, okay? This is what you do. This is 12,345. This is how we write it in Chinese. Okay. I'm going to do the simplified version, otherwise it's too much, okay?
This is the simplified version. The harder version is okay, for this letter I just write down. Now imagine I'm going to use this one to plus this. And I'm going to have a final answer. Okay? That's a freaking essay you're writing just for this stupid equality here. So symbol does make a difference. I don't know how you guys feel about this. I feel great. It's just like the first time I see this, it's like, oh, if I'm going to design that, I couldn't have done it better. Every information is there. Meanwhile, anything not necessary is not there. Okay? This is beautiful and no confusion. Yeah, I can't imagine how people studied mathematics back then. I was trying to write an ancient mathematics book, and it's all words. There's no letter, no symbols, no anything. You know, it's almost like reading a book for something very simple. All right. That's the notation. Let's write down several things. Number one. What do I want to say? Let's see. We want to say how to call it. All right. This is the integral sign. It comes from sum, the letter S. Okay. A is called the lower limit. Okay. It actually means the starting point. B is called the upper limit, which means the ending point. Okay, A, B, is fx is called the integrand, which means the function you are trying to integrate. Okay, but basically that's just the height of the function. And of course, that's the height of the rectangle. Finally, you have the dx, which comes from delta x. But when you let n goes to infinity or delta x goes to 0, let's take delta x goes to 0. It's exactly the same meaning when you have dy over dx, where you're trying to say, okay, I have a change in x, but the change is infinitesimal small. That's everything in this. Okay, it is read by integrate. Actually, the integration of fx from a to b with respect to x. Okay, you can do the integration of any function like x squared, sin x, cosine x, from any interval from 0 to 5, from 3 to 4, 3 to 1, from 10 to 11, whatever. Okay, and with respect to x, this is very important because later, especially in calculus 3, you will have a function which does not only depends on x, but also depends on y, and maybe depending on z. Okay, so then when you take integration, you want to take integration with respect to a particular variable. Let's just say it that way. Okay, so with respect to x, for now it's not important, but later it's really important. Just like when you take the derivative with respect to r or with respect to x, it will give you a very different answer. Okay, it's the same thing. Okay, that's great. That's the notation. Second, what does this stand for? This stands for the net area of fx on AB. But now let's better be careful.
It's better to say from A to B. Okay, let's talk about it. What does this stand for? This is telling you there is a function called x squared. Okay, and here's 1, here's 2, here's a 3. This one say, hey, integrate this function, try to find the area under the curve, all the way from 1 to 3. So this stands for the area here. Number 2, do you know what this means? This means the area under sine x from 0 to pi. All right. Number 3, what does this mean? It means this. But it means more, right? You need to keep going. You need to keep going all the way to 2 pi. So if you go to 2 pi, where do you feel comfortable to draw this? Do you want to draw it with area under the curve? Which clearly is infinity, right? Or do you want to draw the area just between this curve and the x-axis? That's your try. That's your question. Okay. From here, can you see that the old definition won't work anymore? We probably should stop talking about area under a curve. Remember before we said fx is assumed to be positive, right? But in general, fx can be negative. So probably it's not time for us to talk about under anymore. Okay, so what do you mean by that? Let's take a look. What does this notation stand for again? It stands for the sum. Fxi star delta x. It stands for a rectangle. This is a rectangle. Okay, what is that rectangle? Well, this is my x. And this is my rectangle, which is delta x times fxi star. So fxi star is actually the height. Good so far? If this is -1, this is 10, this is 1, this is 10, okay, then the total area is 1 times 10, which is 10. That's how I calculate the area. Now imagine, what if your fx is negative? That means you still have delta x. You still have your fx. But this time, this rectangle is head down. The base is actually on the top. The height is actually at the bottom. If you have to do it, your fxi may be -10. Your delta x may be 1. So what's the total area? If you still want to insist you want to calculate everything in the same way, you have to accept that it's possible for you to have a negative area. Negative area doesn't mean that you don't have an area or you own some area. It simply means the height is negative. Or maybe the width can be negative too. Good so far? So if we just extend our definition for area a little bit, if you extend our definition for under a little bit, we can still keep this notation. It still means the same sum. It still means fxi times delta x. Okay, that's why we want to talk about net area, which means it can be positive, it can be negative, it can be 0. Okay, this is between fx and the x-axis. Sounds good? Okay, so if your fx is above, you have a positive area. If your fx is below, you have a negative area. What if your fx is both positive and below? What's the answer for this one? Well, we don't know the area here. We don't know the area here either. But I do know one thing, actually two things. Number one, this is positive, this is negative. Number two, they are exactly the same, right? So what do you think the final answer is going to be? 0. Why? Because you have a positive part, I don't know what it is, but it's the same as the negative part. You sum them together, it's 0. Okay, very easy to do. Hmm? 1, 2, 3, 4. I have my drawing. Okay, that's the best I can do. 5 and 6. Okay, let's assume the function looks like this. My drawing is bad, but let's just assume all the triangles I draw are the same. Okay, they look exactly identical, even though they don't look like the way it should be. Okay. Is this one positive or negative? Positive. Okay. What about this? Still positive, right? Okay. What about this? Positive or negative? Still positive. All right. Okay. When will the integral be 0? That should go always from 0 to 4. Okay. From 3 to 4, negative. Do you see how to play with net areas? It's pretty easy to understand, right? All right, cool. That's what we have so far. So they can be negative, they can be positive, they can cancel out. With that in mind, we can actually already do some simple integrations. For example, do I want to do that? Let's save it for later. Okay, that's number 2. Number 3, there's nothing important here. We basically want to know how to transfer from an integral sign to a summation sign. Riemann sum. Okay. Basically 2 directions. So number 1, how do you transfer this into a Riemann sum? Okay, it's gonna be limit sum. Okay, height. Okay, width. I got 3 and 1 from here and here. Remember, that's b minus a divided by the whole n. Finally, they're not the same until that n goes to infinity. Sounds good? So if I give you a random integral, can you write down the summation in terms of Riemann sum? Try to do it yourself. It's not a good idea. E to the x dx. Oh, sorry, this is wrong. You can do one more. Okay. Okay. Do you see how we did it? This part come from here. This part come from here. Everything else, just take the limit, write down the routine, and you will be all right. Sounds good? All right, the other direction. Can you write it into the integral notation? Do you know what area am I trying to compute? Work backwards. Okay. Does that make sense? That's basically what you need to know. Okay, it's pretty easy. You just probably need to do 4 or 5 problems to get used to it. They really mean the same thing. After you do that, hopefully you can make the connection that everything here is nothing but the function. Everything here is your dx, basically is nothing but the total length divided by n. All right, that's all for today.